it's just to go into the main aspects of the waves and then focusing into sounds, all right? Mostly resonance for a two open-end pipe or tube and open and close ended pipe. And I'm going to show you the harmonics, and then we can do a few exercises. And I think we can start with chapter 7 on Thursday. Maybe we can do some problems. I have decided to move the exam, okay, because we're going to start chapter 7 probably on Thursday. So let's make the exam on Tuesday, okay? So on Thursday, I can give you some feedback, all right? Or in fact, maybe on Thursday, we can do a review. Let's do that. Let's do on Thursday a review, and then we can start chapter 7 next week on the 19th, okay? We will be losing a class due to Thanksgiving on the 26th. So that means that by the end of the month, we should be finishing chapter 7. And we have 2 weeks in December. That's for chapter 8 and chapter 9. It should be okay. All right. For exam number 3 and the final exam. So again, exam number 2. I'm going to write it here on the board. Where is this? Okay. So exam number 2. Will be Tuesday, the 17th. Chapters 4, 5, and 6. All right. I would suggest that you try and focus on some of the concepts, but specifically with this chapter, you should try to focus on the examples, all right? Because there's not really much to say about waves by themselves. I mean, what you need to know about a wave, right, is that we use a wave to measure a periodic type of motion, right? So you can have a wave going like this, and it has a period and a wavelength. Now, normally we say this is the velocity of the wave going towards the right. We have time. We have the x-axis and the y-axis. Okay? You don't need to know this, but there is an equation for this. The equation for this is the sine or cosine. So in trigonometry, we use sine and cosine to model this type of functions, periodic functions. So it's a periodic function because a period. Okay, and we can use sine and cosine to model the equation for a wave. You actually have to solve differential equation, but let's just put it here. Will be the amplitude times the sine of. That's the linear equation. You don't need to worry about that. The only thing you need to worry is about the omega factor. Normally we say that the period is 2 pi. The period of our wave is actually 2 pi over omega seconds. And the basic equation that we discussed last class is that the period is the inverse of frequency, where frequency is the number of cycles per second, is the inverse of period. We use these factors to measure the periodicity of the wave. But we also have the velocity, right? Now, we know that the distance between the two maximas, or the valleys, so we can actually say this, that is the wavelength. The wavelength is how much one wave is. So, from here to here, all this technically is your wavelength. Okay? So, we want to know how much this pattern repeats. The wave travels at some speed. So, distance is equal to velocity times period. Period is a time for one oscillation, for one period. So if I use this equation, lambda times 1 over period, which will be frequency, is equal to the velocity of the wave. And this works for sound waves, light, electromagnetic waves, right? For any waves, of course for light, that velocity in vacuum will be the speed of light. For sound will be the speed of sound, which is approximately 343 meters per second. Okay? So that's the first equation that I'm for sure going to be testing you guys at some point. Okay? You're going to get a question where you have to use this. In fact, I will do a problem on that as well. Okay? How we relate period with frequency. And then we introduce wavefronts, which are important to know how the wave travels from a source. There is also the idea of intensity and power. So let me show you what does that mean in terms of like, and also superposition, right? When you have the interference. In fact, let's start with that. That's actually more interesting. Very qualitative. Interference and diffraction of waves. Now, that happens with waves in water, with sound, but also with light. And actually, there is a nice experiment that is called the June double slit experiment that studies light as a wave. So if you have light, so let's suppose you have here, you have two slits that are very narrow, very small, and here you have a screen. Okay? The phenomena of interference is that, let's suppose you have water here. Water will go through the slits and they will recombine, the water waves will combine. The same happens with sound. This idea is, for example, or the idea that sound is a wave and travels in every direction, is that you can be in one side of the room and another person can be on the other side on the next room, and you can hear them talking. That's because of how sound bounces, and in some cases it can resonate or interfere. So when we talk about light, we discover that if light is incoming towards there, what we have is, well, as light enters, we have waves forming here, and the same here. As they get bigger and bigger, we start getting points of intersection between the different waves. You see these points? They start intersecting. In fact, this should be more like this. So you can see that. Okay, and here. So they interfere. And if we trace through the points of interference, we get a slit. That's why it's called the double slit experiment. At that point here, we get a slit. There is a fringe. A bright fringe here. And also here is a maxima, here. So, how come you're getting all those bright spots? You have dark and bright. So this is the bright, this is dark, bright, dark, bright, dark, bright, and so on. The same happens below the axis. That's because of how light behaves. So that's called this is called the phenomenon of interference. And you can also have diffraction of light. Interference. The diffraction, normally we use a diffracting grating. Instead of having two slits, you just have on the wall, or you have like an aperture. Very narrow as well. And you can place a slit in there. And then light goes through it and it's breaking into, it's basically what happens, or it's basically why we can see a rainbow during a sunny and rainy day. Because the light of the sun gets diffracted. Refracted, that we're going to study later, and also then diffracted. Right? So we know that happens because light behaves as a wave. Alright? You probably have heard this in chemistry, and if you haven't, that's fine, but light has a dual behavior of light as a wave, as a particle. Alright? So this example that I just drew there is an example of light behaving as a wave. The phenomena of interference. Right? And diffraction. Now, because we know that sound, it happens, there's a similar idea behind sound. We know that waves carry energy, momentum, and force. Okay? So let's focus about the intensity and power. Okay? Again, not much mathematics so far. It's more about the phenomena that you can study waves with. So you can have an antenna okay? And from this point, there's going to be radiation waves. It's going to be radio waves. So the idea with this is that the wave will enclose, it can cover a region. And because, remember that we are in 3D, okay, not in 2D. So we can say that this region is spherical. Like that. So let's suppose that we are trying to measure the power and intensity of this radiation in some given area. So the definition for the power and intensity is that the intensity of the radiation there is the ratio between the power and the area enclosed, this area. And because we're in 3D, this is the area of a sphere, which is 4 pi r squared. There. What are the units for power? Watts. So the units for intensity, watts per meter squared. So far, everything that we are doing here has to do more with light waves or radiation, okay? But I think it's a good way to introduce the idea of a wave. Now, we have mechanical waves. They also follow the same principles, the sine and cosine rule, the period, but obviously for mechanical waves, the speed can be different, right? So let me actually bring a few examples, and I already uploaded this. So let's actually use a mechanical wave and see how we can measure different stuff. For example, I said that a good example of a mechanical wave or a real life wave, right, that we can observe will be in the open ocean when you have a wave. For example, waves generated by earthquakes. So I can give you the speed and the wavelength of it. So we want to compute the frequency. Okay. So let's go into applications of the equations that we have. If they give you a water wave or ocean wave, with a speed of 700 kilometers per hour, and a wavelength of 750 kilometers, we want to find the frequency of those waves. Okay, so how often do they pass on a certain point or area per second? So we just use lambda times frequency is equal to the speed. Right? It's a very simple equation. So lambda is 750 kilometers times frequency is equal to 700 kilometers per hour. So that means that our frequency is going to be in units of 1/hour, but we don't want that. So let's actually solve this problem. There's a calculator here. I get 0.93. So my answer for frequency is 0.93 cycles per hour. But this is not in hertz. To get the frequency in hertz, you have to change the per hours into seconds. So we have to divide, right, that hour into 3,600. Why? We did that in chapter 1, right? Units conversion. So 1 hour is 3,600 seconds, hours per hour, and now I have 1/seconds. 1/seconds is hertz, or cycles per second. So 0.93 divided by 3,600, I get 0.00026. Hertz is a unit for frequency. Okay. The other equation that we studied is, now that we are talking more about mechanical waves, is the following, that the velocity of a wave is also equal to the square root of force divided by mu, where mu is the what? The linear density, right? Mu is the mass of the string or the rope divided by the length of the rope. That's why it's called linear density. and that tension is a force. All right. So if they give you a problem where they give you the force, the mass, and the length, you can use the equation there, and you can get the velocity of the rope. And then a lot of the problems I put here are with the standing waves. So before we go into standing waves, remember that there are two types of waves. Every wave that we've talked about here is a transfer wave, right? Even for this, actually no, not for this, but for this, right? We discuss all in terms of a transfer wave where the velocity of propagation is perpendicular to the direction of the oscillation, right? It's traveling like that, but it's oscillating like that. But you can, so this is a transfer wave. Light is a transfer wave, for example, transverse. Sound. But you can have some mechanical waves where this equation works for this one and also for this one. All right? Actually, no. This one only works for this one. This one is a longitudinal wave. I was making a mistake with standing waves that we're going to talk in a bit. But you can have a spring, and then it goes left to right. The velocity is parallel to the direction of propagation. So that's a longitude. So this will be a longitudinal wave. A good example will be Hooke's law. Or actually, P waves and S waves. When we talk about earthquakes and earth science, we're discussing about seismic waves. The reason why we can study, not predict, but study earthquakes in real life is because we use seismic waves, that they travel all along from the core to the mantle, through the mantle, through the crust. There are two types of waves because P waves, they can travel through solids and liquids, but S waves only through solids. And P waves are longitudinal and S waves are transverse, as far as I remember. Yeah. So we study this difference of arrival time, and that's how we know the epicenter of the earthquake, right? We use triangulation. Seismographs, that's the idea behind a seismograph, all right? So it reads the waves, okay? The amplitude and then the intensity. That's how we get a Richter scale for earthquakes. If you guys are not very used to this, because here in the US, you guys, well, in this part of the US, you guys don't get earthquakes, right? But back in South America or in the Western coast, there are. So that's a necessity to know the physics and the idea behind of how or when can an earthquake happen, right? All right. Then the other concept was the Doppler effect, right? So let's study the Doppler effect again. Now I'm going to do you a few graphs. I described that last class. I don't know if that was enough. So I'm going to draw you a picture, and I'm going to use both sound and light, because the Doppler effect for waves can be studied in both. Now we know that sound, just like light, is propagated through a wave. But the way it works is a bit different. Not in terms of like the equation, but when you can see one and the other. Remember that sound needs a medium to travel. Light, on the other hand, does not. So that means that we can perceive, we can measure Doppler effect, redshift of galaxies, but we cannot do the same with sound in space. The phrase, nobody can hear you screaming in space, right? So that's the idea, right? Sound is a medium, light does not. So what is that Doppler effect? Actually, We'll see. Hopefully we can get into tubes because there's a few things that we have to discuss here. There are no problems in here. I mean, there are a lot of applications, but we are not going to discuss in detail, in terms of mathematics, the idea behind the Doppler effect, all right? But just remember this, or just focus on this. Imagine you are an observer here. And then you have a light source. Can be a star, a galaxy. So just have a light source there, like this. Now light propagates as a wave, right? But now we're saying that the light is moving towards you with some velocity. What happens is that as light travels through you, towards you, sorry, what happens is that this wavelength becomes smaller and smaller and smaller. Not maybe in amplitude. In amplitude it doesn't. What happens is this. We have a wave. Oh, there it is. So the amplitude of the wave didn't change. The wavelength decreases towards here, right? The wavelength, so lambda, that's a symbol lambda for wavelength, decreases. Now, why did I use blue? Because this is called the blue shift, meaning that the intensity that you're going to receive is greater, and we can measure this by the change of frequency. The frequency measured by the observer is equal to the frequency of the source times the speed of light plus the velocity of the source divided by the speed of light minus velocity of the source. Okay. If it was a sound on Earth, so this is in space, right? Or if you are looking from Earth towards the universe, right? Space exploration, redshift, or blue shift, right? Redshift would be if this guy was going on the other way. So if now we have this with the same speed, what happens is this. Now I'm going to use red. So the wavelength doesn't, the amplitude doesn't change. The wavelength, however, towards here, right? You are measuring respect to this guy. So the wavelength increases. If the wavelength increases, then the frequency decreases. So this is for this case. Now here, for this case, the frequency measured by the observer is the frequency of the source times the speed of light minus now the velocity over c plus the. There it is. Do you need to know the equations? Maybe just to read the equation, but you're not going to be using them in any problem. All right. You can, however, you can actually predict or you can actually estimate the frequency of the source or the velocity of the source if you know the real frequency and the observed frequency. Okay, so that's how we measure the redshift. The redshift, when you read that in an astronomical journal, it's basically the idea of light changing its frequency due to moving away or towards the observer. But sorry, for redshift, as you see there, is moving away. That's how we know that the universe is dynamic. It's moving, everything is moving away from each other. So what about sound? For sound will be the same. Let's suppose these were sound sources. For sound, we're going into sound now. The frequency, if the source is approaching, actually, I want to write that. Get that quick. Nah, it's better if I put the difference. If not, you're going to get confused. The source approaching the frequency read by the source, by the observer, if the frequency of the source, not C now, velocity of sound plus velocity of the source, or velocity of sound minus velocity of the source. Speed of sound. So you just change the speed of light to speed of sound. Okay? So you're going to get a question where I'm going to ask you to discuss how do we study the Doppler effect, or what's the difference between the source moving away or moving towards. You can use the ambulance example I talked to you guys about last class, and now I'm recording the class. I didn't record the last class, right? Or you can use the light example, all right? The person who discovered this in the 1920s was Edwin Hubble, by observing the redshift of galaxies. And then we extrapolate that knowledge into sound. And we know there is a Doppler effect as well for sound. All right? Clearly, it's more obvious in astronomy because the speed of light is very large. It's 3 times 10 to the 8. 300,000 kilometers per second. While the speed of sound is only 340 meters per second. It's nothing. Have you ever wondered, for example, right? Think about this. Imagine you are witnessing, you are far, when you are in the 4th of July, you go to the Central Park in New York, hopefully next year. Yeah, next year should be fine. You go and then you watch the fireworks, right? If you're far from Jersey City and you see the fireworks, the first thing you will see will be the light and the explosion. And then you will hear the sound. That is the best way to show you the difference on the speed between the light and the sound. Light gets way faster towards us, and we look at it, than the sound, right? Or lightning. You can watch lightning, and then a few seconds after, you hear the thunder. So the same happens with this. Okay? That's why normally you can start seeing lightning before rainfall or the thunders start, right? And that happens a lot, in summer especially. So now we're talking about sound. So before we talk about sound, we need to introduce the idea of standing waves. So let me see the slide here. So we discussed about this. Remember that these slides are better, guys. Don't worry about, well, here is the equation. We talk about superposition as well. Don't worry about this, okay, or this. We talk about the longitudinal waves, and now we're going to sound waves. The Doppler effect here, guys. Don't worry about, okay, here's the equation for intensity. Again, you're not going to be using that. You're not going to be using this as well. This is decibels. If you are interested in where do decibels come from, guys, you may want to look at this, okay? That's how we measure sound in real life. We don't talk about, oh, the intensity of the trumpet is something watts per meter square. We talk about decibels. So there's a way to get from decibels to meters, watts per meter square. And there is the equation there. It's a logarithmic equation, so don't worry about that. There's a Doppler effect there. That's the one there. And that's the equation. That's the equation of decibel. That's the equation. That's the one for light. and then we're going to, we talk about interference already, okay? And the wavefronts. Let's talk about standing waves. So, when we talk about transverse waves, we're talking about a wave that is free to move on either side. Ocean wave, light, sound, right? Let's suppose now we have a wave that is fixed in a location, but it's oscillating with time. The best example would be the waves on the string of your guitar. If you guys play a guitar or a violin or whatever, the string is fixed, right, in two ends. And then you exert a very tiny force to create a note. So you see, as it says there in a musical instrument, that you have vibration of columns of air. And you basically see what the figure that is showing you. Okay? So the idea is to think how many wavelengths can travel in one standing wave. Now, there is a whole concept of group velocity that we can introduce. But if you see the figure there, they give you a nice illustration of a standing wave and a normal wave. And as you can see here, what you see on the standing wave here is just what? Half the wavelength. And that's going to be important when we talk about the resonance in tubes. When you have the resonance in a tube with two open ends, and the tube or the pipe can be of length L, we have different harmonics. The first harmonic, the second harmonic. The idea with the fundamental or first harmonic is that you have half the wavelength contained. If you have two harmonics, you have the wavelength totally contained inside a tube. If you have three harmonics, it's only 2/3. So there is a rule for that. There is a rule to know that, we know that we're talking about sound. Now we're talking about sound. So there is a nice rule to get the wavelength depending on the harmonic. And that's why I'm not sure they told you that in the lab. If they didn't tell you that in the lab, now you will know. Okay? The equation has to do with the number of harmonics, right? Because a standing wave can have several harmonics. Let me see if it's in the slides here. If not, I will draw in the board. Oh, there it is. Right? So you have one harmonic, two harmonics, so that's a total wavelength, three harmonics. So there is something called the node and the antinode. The nodes are the points of intersection. All right? Here. The antinodes are the crests, the peaks. So that once you understand the first harmonic, it's easy to get the idea for the other situations. And this is the one that we're going to use for the two open end pipe or tube. Okay? Because let me show you, I don't know again if they show you this in the lab, but let me draw you a few pictures. Okay? So I'm going to leave that in there. I want to be drawing something on the whiteboard, but the idea was that you can get the speed of sound by understanding how a wave behaves inside a tube. So for a two open-end tube, so we're going to do a two open-end tube. What you're seeing right now are the harmonics, right? The fundamental harmonic or first harmonic, and then you have the second harmonic and so on. So it has to do with how the wave enters the tube and how it leaves, right? Because in a open-end tube, there is not really there's only one node. That's the thing with an open-end tube, okay? And there is no a point where the wave will bounce back. So let's put it here. Remember that the harmonics, we label them as n. N is your number of harmonics. We don't really care or count the number of antinodes, only the nodes that end there. There and there. Okay. Now I wanna open the. Oh, that looks so bad. The symmetry. Let me just. Okay, that's slightly better, but still not happy. But that should do. It all has to do with the number of nodes. Anyways, so for an open-end tube, you have one node here for the fundamental frequency and two nodes in here, right? And then for another tube, for an n equals to 3, right? You will have 3. So normally what I do is like that, and then you start from here. 1, 2, 3. So 1, 2, and then that should be here. Too long. There. There. So a wavelength and a half. A wavelength and a half. Here is a total wavelength. So the length of this tube is the total wavelength. Here, the length is equal to half the wavelength. Here, the length is 3/2 of the wavelength. So we have here 1/2, 1, 3/2. So we have a rule for the lambda. The wavelength will be twice the length of the tube divided by the harmonic. Right? Here the wavelength is 12. Here is L. Here the wavelength is 2L divided by 3. So I always have 2L. And here will be what? 2L divided by 2. Which is 8. So the general rule is this. Now, we have the wavelength, and you know what's the key on standing waves in a pipe? Is the frequency. We want to study the resonance. So, why? Because if you're given the length of the tube, you know the wavelength, and you know the speed is the speed of sound. So guess what? We can go back to this equation. We can go back to lambda times frequency equals to the speed. So I want to get my frequency. My frequency will be 1 over wavelength. The inverse of wavelength will be, you change that, n over 12, and this is the speed of sound, times the velocity of sound. This is the equation that you have to use in that. So, clearly, depending on the harmonic, right, you can find the wavelength. And if you have the wavelength, or if you have the two different harmonics, you can find the difference on the frequencies. All right? So certain wavelengths will reinforce each other. That's resonance. To obtain certain tones. Okay? The points of resonance are the ways where they reinforce. That's how you get the tones. Let's do a problem. Give you here a pipe with both ends open with a length of 0.8 meters. They give you the velocity of sound, 340 meters per second. They want you to find the frequency of the second harmonic. So, we have the equation already there. You want the equation of the second harmonic. So, if you have the pipe with length 0.8 meters and you have the velocity of sound 340 meters per second and you want the frequency on the second harmonic, you use the equation. In the second harmonic, n is equal to 2. So it will just be the velocity of sound divided by the length. Right? Here. The frequency on the second harmonic will be n over 12, which is 0.8, times 340. And if you do that division, you get 425 hertz. This is a problem that you for sure are going to have to learn. So, do you really need to know all this? Not really, but it's good that you know where it comes from. Okay? Let's talk a little bit about, let me see. Pipe close, this is close, open point. So they can also give you the frequency and ask you for the speed of sound. Let's do this one actually. So now they give you a pipe because then we're going to talk about, remember, right, there are two cases. This is a simple case when the wave doesn't have so much interference. But what happens when there's resonance with a tube with one end open and the other one closed? All right? We're going to do that in a bit. But for now, let's do another problem using this. So again, the formula that you need to remember is the one over there. Okay? So they give you now, let's look at it here, pipe. So you have a pipe or a tube, doesn't matter, with length 0.92 meters. And they give you the frequency of vibration 584 hertz. Oh wait, but we need to know what harmonic is. In the second overtone. So that's on n equals to 2. So in the second overtone. So in that case, what I will do is I will use the equation. 584 equals to n over 2 times 0.92 times the speed of sound. Right? 2 and 2 cancels, and you should get something appropriate. Wait. The second overtone. Wait. Should that be? I did that multiplication right. N. N over 12. Wait. Okay, wait a second. 584, the vibrator is in the second overtone with a frequency. Sorry guys, I'm just making a mistake here, I think. 137. It's none of the answers. Pipe that is pointed to open at both ends. So N over 12. Second, okay. Like that. Yeah, I believe maybe what they mean is a close, open-ended, because that would, what you know, for L, no, but that wouldn't make sense because that would be much larger. The speed of sound. I have to double check that problem. That's a problem from the worksheet. It's not giving me the answer. Why? 584 by raising the second overtone. The second overtone should be n equals to 2. So 0.92 meters long. What's the speed of sound in the air in this pipe? See what they're expecting. So 584. Oh, second overtone can be equals n 3 times 2 times 0.92 divided by 3. For some reason they're expecting n equals to 3. Why is that? What happens in n equals to 3? Okay, so problem 7. Okay, so here there's a mistake. If you guys decide to do the problems, this should be the third overtone. If not, you're not going to get the answer. The third overtone, now it will give you, right? The second overtone is when you have the second harmonic. The third overtone, however, that will give you the answer that a more reasonable answer. So 3 over 2 times 0.92 times the velocity of sound. So again, if you do the calculation, you get 358 meters per second. So that's more reasonable. Okay? There are some problems where we have to be careful. Okay? Let's talk about a pipe where, and I knew this couldn't be a pipe with an open end and a closed end, because that's when the wavelength becomes way different, okay? Very quickly, to show you the graphs, okay? When you have a pipe, with one open end and one closed, like that. So the difference is that the wave at this point is going to bounce back. It's not freely moving from one end to another. So you can say that on the first harmonic, it looks like this. So the wave can continue here. So that looks like, if you compare it to this, right? That looks like you cut this part, right? Think about it, there, right? Or in this section. All this is wave. This is half the wavelength. So how much is this? Wavelength divided by 4. So you are cutting now the wavelength. So if this is L, the length of the tube, the length of the tube is equal to lambda divided by 4 for the fundamental frequency. Fundamental. Okay. So what about with the other cases? All right. On the other cases, what you're gonna see that the wave enters like this and then leaves like this. What do I mean by that? Let's go to the second harmonic. So now I want to draw the pipe again. So now it's going to enter like this. Right? Like this. Okay, yeah. So like this and like this. Okay. So it's not going to converge now. Now it's going to be like that. Like that. Okay, so this looks like what? That length of the pipe now is going to be how much? So now we have 1/2 plus 1/4. Half a wavelength plus 1/4 of a wavelength. If you do the math, you get 3 lambda over 4. But that's equal to the length of the tube. Therefore, lambda is 4 over 3 L. Here, lambda was 4L. All right. So for the first, actually, this is the difference though. So we don't call it, let me put it here. We don't call it here. So this is the fundamental. This actually, if you think about it, the note is inside here. So we don't call it harmonic anymore. That was the problem here. So let's call this there you are. When you have a pipe with both ends open, we call it the first harmonic or note. Here you have now a fundamental frequency, and this one is called the first overtone. Here is where we use overtones. So this will be your first overtone. Okay. So we have now the frequency. Okay. So now we want to know what is the relationship between the fundamental frequency and the speed. So let me just bring something out. Because we found one for the okay, yes. So lambda equals to 4L. Here lambda equals to 4L divided by 3. And then the second overtone will be 4L divided by 5. So it's not exactly the same as harmonics. In harmonics you can have in 1, 2, 3, 4, 5. There is no problem. They can be even and odds. For this, what we see is that the overtones are only octs. 1, 3. If I do the one for, so for example, it will go like this, and like this. So like this, and like this will be lambda plus lambda over 4. Ah, that's a good one. So let's do it here. If I do the same, so I'm doing the fundamental, the first overtone, and here I'm going to do the second overtone. So in the second overtone, right, you will have this. You have lambda like this. So lambda going like this, and then like that, and then like that. So what's that? That's lambda plus lambda over 4. So the length of the tube is equal to lambda plus lambda over 4, which is what? 5 lambda over 4. So your lambda is 4L divided by 5. There you are. Over 5, over 1, over 3. So for an open and closed pipe, the equation for frequency is N over 4L times the speed of sound. But guess what? N has to be oct. So 1, 3, 5, 7, and so on. Okay? That's what we don't call it harmonics. That's what we call them overtones. So actually, let me see here. Yeah, so let me see something. You don't use overtones in both pipes open in both ends, but this can be the case though. Yeah. So in the problem that we did before, they refer to the second overtone. The second overtone will be when n is equal to 3. But that doesn't make sense. Overtones only make sense in this type of situations. You don't have harmonics anymore. You have overtones. that comes from the musical instrument. Okay? So now we found the equation for both, for a two open-end pipe and an open and closed-end pipe. Okay? You only need to know about the equation, not too much about the graphs. The graphs are used to model and to prove the equation. All right? Remember that the equation that we get for the frequency, so now I can erase this and give you the equations. Erase this, it's fine. So we can make a difference for a two open-end tube, for a two open end, the frequency as a function of the harmonic is n/2L times the velocity of sound. But for an open closed, so open on one end, closed on the other end, the frequency n odd is equal to n divided by 4L, speed of sound. But let's specify that n can only be 1, 3, 5, and so on. Let's see if there is anything here. Well, I mean, that's easy. It asks you, what's the length? And we'll finish with this problem. And the good thing is that we can do more of this on Thursday before we do the review. So the review will go from chapter 6, then we go to chapter 5 back, and then chapter 4. Okay? We do the review like that on Thursday. So, oh yeah, but Thursday I'm going to be... That's fine. What's the length of the shortest pipe, closed on one end, open at the other end, that will have a fundamental frequency of 60 Hertz on a day that the speed of sound is 340 meters per second. So now with a closed pipe, for an open closed pipe, they want the fundamental frequency to be 60 Hertz. So 60 for this guy, right? Fundamental frequency is n equals to 1 over 4L times 340. So here L will be 340 divided by 240. So that should give you 34 over 24, 17 over 12. That probably should give you 1.42. Yep, that's the answer, 1.42 meters. So these are probably the main equations of today. Okay, we will do that problem on the lab again so you guys can understand it better. Because in that problem of the lab, if you remember, well, I think I show you, right? They give you the two harmonics, right? If you know the one harmonic and the other harmonic, you know the distance, and if you know one is open-ended and one is, it was an open and closed because you had water in there, right? So that was just lambda over 4, the different harmonics. And then you just have to compute, if you have the lambda and you have the length of the tube, you can find the velocity of, they give you the frequency of the fork. So now you know why I did what I did that day. Okay? Okay guys, I'm going to stop the recording. And